Welcome back to Bodhi Unified Flow. Today, we're diving straight into something absolutely crucial for any structural engineer. We are unpacking the Blueprint Revolution, a 4-year roadmap to civil mastery, specifically for BE and BTech civil engineering students. Right now, our total focus is on the skeleton. We're going to explore the pure physics of building safely by tracing how loads, dead, live, wind, and seismic travel relentlessly from the top slab all the way down to the foundation.
Because here at Bodhi Unified Flow, we simplify complexity and amplify performance. Whether you're a first-year student just wrapping your head around the math, a senior ready to design integrated systems, or an enthusiastic practitioner wanting a refresher, this explainer is built specifically for you.
Here is our agenda. 1. Understanding structural load paths. 2. Gravity and lateral forces. 3. Slabs, the horizontal origin. 4. Beams, columns, and flexure. 5. Foundations, the earthly anchors. And 6. Mastery, summary, and references.
And our learning objectives are pretty straightforward today. We want to grasp structural load paths and physics, differentiate gravity and lateral load types, trace horizontal origins in slabs, analyze the vertical descent via beams and columns, and finally, understand foundation termination. Let's get right into it.
Section 1. Understanding structural load paths, the central nervous system of design.
You can really think of the load path as the central nervous system of structural design. A building isn't just sitting there. It is a dynamic system continuously fighting a war against gravity and environmental energy. The journey of any force begins at the slabs, transfers to the intermediate beams or joists, plummets down the columns or shear walls, and finally terminates in the foundations. In this route, it's governed by 3 non-negotiable principles: clarity for direct routes, continuity to avoid stress buildups, and redundancy to prevent catastrophic, progressive collapse.
Section 2. Gravity and lateral forces, the cast of characters.
Before we actually trace the path of these forces, we really need to meet the cast of characters. There's a striking contrast between our primary gravity loads. Dead loads, the self-weight of concrete and steel, are permanent and static. Live loads, on the other hand, are highly variable. Think occupants, furniture, movable walls. Engineers use standards like ASC 7 and IS 875 to probabilistically estimate these. So, for example, a residential floor might require 40 pounds per square foot, while a crowded public assembly area demands 100.
But gravity isn't our only enemy. We also face lateral forces, wind and seismic activity. Wind exerts massive horizontal pressure on a building's geometry. And seismic loads, well, they're even more complex. The base shear equation, V equals CS times W, reveals that seismic forces are inertial. Following Newton's second law, a heavier building with a massive dead load actually attracts a devastatingly higher earthquake force. So ironically, adding material might make a building stronger, but it also makes it a much bigger target.
Section 3. Slabs, the horizontal origin.
So where does the internal journey truly begin? Right here, at the primary horizontal plane, catching all those gravity loads. The crucial point is how the load actually decides which way to go. This is dictated by the shape test, or the aspect ratio of the slab bay. If the ratio of the long span to the short span is greater than 2, it's a one-way slab. The force basically takes the path of least resistance, traveling directly across the shorter distance, making the slab bend like a single wide beam. But if that ratio is 2 or less, it acts as a two-way slab. The force spreads out orthogonally, bending the slab downward like a dish, which means you need a completely different grade of steel reinforcement.
Now, depending on architectural needs, we might use a flat plate system with 0 supporting beams underneath just to save headroom. But removing beams introduces a massive risk: punching shear. Because all the weight of the slab concentrates onto the tiny surface area of a column, it can literally act like a paper hole punch, driving that column right up through the floor. To stop this, structural engineers will strategically thicken the concrete around the column using drop panels, or flare out the top of the column with capitals to distribute that aggressive force over a much wider perimeter.
Moving on to Section 4. Beams, columns, and flexure, the vertical descent.
Once that horizontal plane organizes the forces, the load transfers straight into the beams and columns. And inside the beam, extreme flexural physics take over. When a beam is loaded, it naturally wants to sag. The top fibers are brutally compressed, while the bottom fibers are stretched in tension. This internal warfare is governed by the normal bending stress formula, sigma equals my over I. The bending moment, the distance from the neutral axis, and the cross-section's moment of inertia literally dictate whether that beam holds or snaps.
This is exactly why we bury high-tensile steel rebar at the bottom of a concrete beam, because concrete on its own is incredibly weak in tension. To make this abstract math visceral, just consider a standard two-story residence. A single beam carrying just a 100-square-foot tributary area, meaning its designated share of the floor space, with standard residential dead and live loads, is silently shouldering a massive 16,000 pounds. That is the weight of about 4 average cars resting on one single wooden or steel member every single day without yielding. It's wild to think about.
From the beams, that 16,000 pounds transfers straight into the columns. Now, columns are designed for pure vertical compression. But interestingly, tall, slender columns don't fail by simply crushing under the weight. Nope, they fail by buckling, a sudden, violent sideways bowing that's governed by Euler's buckling load equation. The absolute critical factors here are the length of the column and how its ends are restrained. If you rigidly fix the ends so they can't rotate, you can effectively quadruple the column's resistance to buckling.
But hey, we live in the real world, where wind and earthquakes make buildings sway. And this brings us to the terrifying P-delta effect. Imagine a column is carrying a massive vertical load, and a gust of wind causes the building to deflect horizontally, even just a tiny bit. Suddenly, that vertical load is off-center. That off-center weight multiplies the bending stress exponentially, creating a secondary moment. It's a vicious cycle of geometric nonlinearity that can lead to rapid instability if the engineer hasn't designed enough lateral stiffness into the structural frame.
Section 5. Foundations, the earthly anchors. Terminating the load path.
After surviving that perilous journey down the skeleton, the accumulated load finally hits ground zero. And engineers don't just pour concrete and hope for the best. The foundation choice depends entirely on the Earth's bearing capacity. If the surface soil is firm and stable, we use shallow spread footings that rely purely on direct contact pressure. That's end bearing. But if the loads are immense, like in a skyscraper, or the surface soil is just weak, we gotta plunge deep. We drive piles 15 to 100 feet or more into the ground. These deep foundations support the building not just by resting on hard bedrock, but through skin friction, the massive frictional resistance between the sides of the pile and the surrounding dirt.
And this builds into an even more complex reality: soil-structure interaction. Textbooks love to assume a building is fixed to a rigid, immovable base, but the Earth is a living, compressible thing. The foundation and the ground actually act as a coupled, interactive system. As the building pushes down, the soil settles. If the soil settles unevenly, which we call differential settlement, it acts like a giant lever, violently forcing new, completely unanticipated stresses all the way back up into the beams and slabs we literally just finished calculating. A safe design has to anticipate how the Earth will breathe and shift under the building's weight.
Section 6. Mastery, Summary, and References. The Academic Blueprint.
So how does a young engineer learn to actually command all these forces? Well, we map the pure mechanics we just discussed directly onto the 4-year roadmap of a civil engineering degree. In year 1, students build the mathematical language and applied physics required to even perceive these invisible forces. Year 2 dives straight into mechanics of solids, learning exactly how materials stretch, bend, and yield. By year 3, students apply design logic, using structural codes to detail reinforced concrete and steel, countering the very flexure and punching shear we just analyzed. Finally, year 4 synthesizes it all into integrated systems, encompassing deep foundation engineering, earthquake dynamics, and complete computerized building models.
And look at what we've achieved together in this short explainer. We have successfully demystified the central nervous system of our built world. We outlined how forces flow seamlessly from the sky to the soil. We defined the fierce characters of dead, live, wind, and seismic loads. We mapped the shape testing of horizontal slabs, evaluated the brutal internal flexure of beams and the buckling risks of columns, and finally, we anchored our understanding deep into the friction of the Earth. We've taken massive physical complexities and distilled them into a clear, unified flow.
Our understanding today was grounded in key engineering hubs and codes like Civil Era, ASE 7, IS 875, IC Knowledge Hub, Woodworks, and Earth Engineering. This ensures what we build today survives for generations. Mastery of this structural skeleton is the ultimate revolution in engineering. It's literally the power to look at an empty plot of land and envision an invisible, robust network of forces capable of holding up the sky. So I leave you with this final thought. As our cities grow taller, our climate gets more unpredictable, and our materials become more advanced, are you ready to apply these principles to ensure the skeleton of our future society is robust enough to survive the truly unexpected? Keep learning, keep building, and I'll catch you in the next Unified Flow.